Hello everybody, how's it going? Welcome back to the stream. It's cool, we retained some viewers from the massive weekend from the influx of my YouTube video. That's awesome, cool. Okay, so for today, it's gonna be a bit shorter stream again. Yesterday was an exception, but we made amazing progress today. So for today's stream, I want to start with just showing you what we did yesterday for those who haven't been there, and then we go from there. Oh, thanks for the tier 1 sub, cool. And thanks for the bits during while we were waiting for the stream to start. Okay, so let me show you where we left off yesterday. So, as you can see, we have finished the ALU. At least I believe we have finished it. It seems like ours is working. I believe Ben Eder had actually problems with his, and we will continue with watching his troubleshooting video, but I believe ours is actually working. But I'm not sure what kind of issue he has. Maybe there's an issue I don't realize that we have. So yeah, thanks for the DM. Okay, let's see. You have a really long intro before the stream starts. Yeah, I'm sorry. At the beginning I did it shorter. Now I decided to do a bit longer. I don't know what is a good time, because it would be cool if people are there from the start, especially if it's shorter streams. But that's why I think a 15 window is maybe okay. I guess if everybody knows it's a 15 window, then I don't need to rush and can chill, you know. So maybe that's okay. All right. Welcome back, the blind hacker, and thanks for the cheers. So, look at this. Let me turn on the power. Okay. So you can see here already the ALU output on these LEDs. And basically what we can do now is in both registers, they are always coming up with set to 1111. And as you know, all ones is the 2's complement of 1. So this is basically equivalent to a negative -1 in binary, which means if we use the addition of the ALU to always add this to the other register, we basically continuously perform a -1, -1, -1, -1, and we then count through the whole thing here. And you can already see the output here. So here everything is glowing except the last LED. You can kind of not quite see that. Oh, let's see. My camera might be off. Wait, let me check. Sorry. I forgot to start that camera. 1 second. Okay, yeah. So this value, no, wait, it's this value down here -1 by adding the 2's complement here will result in all set except the last one. Yeah, there we go. So here you can see that the last LED is not glowing. Anyway, so what happens now if we execute the clock? Currently it's configured in a way that this register has the input enabled, so it will read anything that is currently on the bus, and the ALU is outputting its result on the bus. So right now, so if you look here in the register itself, it's 1111, so the highest value, but on the bus it's already -1. So if we execute the clock, it will move now the value with the -1 into this register, which means the ALU will then calculate -1 from that and put that on the bus again. And with the next clock, we move that value in there. And through that, we basically circle here around and always decrement this value. So if we execute the clock by hand, we can see slowly this register counting downwards in binary. And the cool thing is, we have a clock, so we can let this run even automatically. Oh, this was quite fast. So here, you see the clock blinking here, and it's slowly decrementing. Isn't this awesome? So this we finished yesterday in our massive 7-hour stream or so. And it seems to have worked. I also believe we found the issue that Ben Eder had. I think he switched some connections on these chips here, and I think we did it correctly. But yeah, like I said, we will see where Ben Eder is. But let me turn this off really quick again, because I have something else to show. First of all, let me see what arrived. It's a replacement unit. Okay, so this is the FLIR thermal camera. I had ordered one already last week, and then it arrived and then it didn't work. Now this one worked. At least it worked once. I hope it works now live on stream. If it doesn't work, I have a backup video made. Okay, so let's see. I have here my phone that should be able to perfect. So you can see here my phone on the screen here. Maybe, yeah. And then we can turn the FLIR on. And please work. Please work. Okay. Oh, yeah, it worked. It turned on. It's so scary because in the beginning it stays red, and then at some point it starts turning green, and so it's like a huge wait moment to wait. Ah, crap! It's already pretty warm. Those chips there. Come on, cool off. Okay, so this, I guess I did the order wrong there. That sucks. But I think we should still be able to see it. The scale is right now pretty strict, I guess. So if we change here, if we go up here to like, let's go here 50 or something. Now the color is still like very close. So let's see. Okay, so let me turn this on again, and then we watch this for a little bit. Maybe let's also move this. Let's move this for now over here for a moment so that you can compare. And then let's turn on the power again. Now you see it blinking, and you see immediately the color slightly changing. And if we just wait for like a minute or so, oh, you see the red coming up there on those bus transceiver. This one in the middle there, so this one here, this one has to run all these LEDs. So there's a lot of current flowing through that one, and so it will become quite hot. So we can, I mean, relatively. So we can see that it's like roughly 40 degrees compared to next to it like 30 degrees. And so we can now observe how, because of these calculations and driving those LEDs and stuff like this, the thing is slowly heating up. This app can also show, oops, those are my test video. No, back. I screwed up. Back. How do I go back? I meant to go color here. So we can also look at this in different colors. But yeah, it's clear. You can clearly see how the those ICs get pretty hot from running. Isn't that awesome? $47 degrees, 45 degrees, this one. Yeah, this one gets the hottest because it's outputting to those LEDs, I believe. And I guess it gets also worse if we crank up maybe the clock. I'm not quite sure. But yeah. Okay. Glad that I spent 400, no, not quite. Yeah, 400 euros for this gadget for the stream. I hope you enjoyed that. But yeah, we will use this more because it might help us with debugging. If chips get hot and stuff like this will be fun. I plan to mount it like here on the top so that we can easier switch to it and easier look at it, so I don't have to hold it. And I think that would be really cool. So what do you guys think? You like that? You look like Andrew Shear. That's a first. I haven't heard that. I actually don't know Andrew Shear. I don't know who that is. I'm usually told that I look like Michael Cera. Okay, so we exit the app. Now let's be careful with this device that so easily breaks. let's unplug it. Okay. Oh gosh. Awesome, right? And yeah, so right now it's running super fast. As we know, the maximum frequency this currently runs at is 500 hertz. And so in 8 bits you can store up to 256 values. 250, it counts up to 255 basically. So which is roughly half of 500 hertz. And so in each clock cycle it will decrement once, which means with 500 hertz it will be able to count to 255 like twice per second basically. And this is actually kind of what you can observe. The front LED now is indicating like the highest bit, and this should turn on and off twice per second. And so if you count this, like, yeah, you should see that this LED down there is blinking twice per second roughly. Okay, let me quickly catch up with chat because while I was holding the camera I didn't the wire stripper. Okay, so let's see. Thanks for the bits again. Production quality, I hope so. What happens if you turn off the lights? Will we be able to see the LEDs better? Yeah, basically, but it's also a problem of the angle. Like this one is exactly as bright as these other ones, just the angle is a bit different with the camera. I've ordered different LEDs. They should arrive sometime this week that have hopefully a wider spread, and then it should also be better to see. This is neat. Yeah, I think that's the best reaction to that. What are you using to get the phone's display onto the stream? The app is called like HTTP streaming. It's like an open source project on GitHub, and you can also screen stream HTTP, I believe. Screen stream screen stream over HTTP. There we go. The code is on GitHub, and you can also find it in the App Store. It looks really cool, and it works flawlessly, as you can see. It basically opens up a web server with just an IP and port, and you just point your browser at it, and then you get a live stream of your phone on the browser. Thanks for the sub, DevHops. Does the ALU write directly to the main bus in this design? Yes, but we can enable, disable this. So this cable here is the output enable. So if we disable that, I mean, now it's also stopping because now the value is not being put onto the bus, which this is reading again. But yeah, so with this we can enable or disable the ALU to write to the bus or not. In my old design on the register inline, you have to get a haircut. I hope I can make it back before the end of the stream. Will there be a more serious version of your beauty tutorial? I mean, I like the experience. That's the main problem why I can't give you any more serious one. I mean, it's as serious as I can do it because I have no clue. Did you use Chromecast? No, I was not able to get my PC to allow casting. I don't know what it is. I tried to troubleshoot for a couple of minutes and I couldn't figure out why Miracast or whatever it's called on Windows didn't work. So I couldn't use the casting feature of the phone. And then I found this HTTP one, which is great because then it's just a website, and with the streaming software OBS, you can add a browser source, and so it will just overlay like a website over your stream, and so it's easy to just overlay the website where the stream is coming in onto the stream, and it works perfectly. Can I get a quick pen modding tip? I don't know. What tip do you need? It's a very broad question. And can it run Crysis? The old joke. Okay, I have something else for you. I have something else to show before we head into the video. Do you see that smiley face back there? See that smiley face in the corner back there on the table? guess what is in there. Let's do an unboxing stream. Gotta be careful here with some kind of papers in there. Looks fine. All right. What do we have here? I have no clue what's all in here. So what do we have here? Cable. I have no clue what I ordered here. What is this? Oh! Okay, so these are just some additional probing stuff. I was especially interested in these tips here because they have like the crap. Sorry, I didn't show this at all on camera. So these are here just some things that you can attach to, for example, the power supply or a multimeter. And I was especially interested, and I especially wanted these ones here because they have like this spring inside, so you can like hook around the wire. So that's good for measuring if you don't want to hold it and stuff like this. So that's what I ordered. So what else do we have in here? What is this? I don't remember. Oh, okay. So here we have a first useful tool for us. Hopefully it will be useful. Okay, come on, go out of here. Awesome, we have some a new pair of like, I forgot what is the English term, I forgot, but this one has like a more pointy end with it, which is curved, so it's easier for me to like go in there and maybe bend the cable or lift the cable out. And I hope this is better because the one I had here was just like a broad one. However, giving you a product review right now, I actually really don't like the mechanism of this one. I didn't actually pay attention to this at all when I ordered it, because this one gets really close before you have the spring effect. So I really don't like that actually. I was hoping it would be the same like this one, where it would open up a lot and has the spring inside here. What a cheap out design. That's terrible. Maybe you can bend this to make it a bit more. Yeah, but nah. I might look for another one. Don't like this theory, but it should still be helpful. It should still do its job basically. So yeah, I hope this is helpful. See, I thought this is the same like line of clippers, but it apparently is not. I don't know. I just paid attention to this kind of color, so maybe there's a different even line. They have so many different like classifications and stuff. Okay, so what else do we have in here? Okay, so another thing we have here is a better multimeter. In one of the earlier streams, I failed. It was a real bad fail. I have this other multimeter here. I have this for quite a while now. It's an extremely basic multimeter, and I tried to measure a capacitor with it until I could have sworn I did it the previous day already, and so I tried to measure it, and then I couldn't measure it, and people were telling me it can't measure it, and I didn't believe them, and at some point I realized, oh, it's right, I actually cannot measure capacitance with it. So yeah, I decided to buy a differently one, and then I asked Stream, and I thought about buying like a big fluke one because I don't know, just have a professional one that will be useful for basically a long time. but then I decided to go with this one here. This one was also recommended by a viewer. It seems to do a pretty good job for in general, and should be good for like electronics work. So let's hope that this was a good purchase decision. Yeah, so it's an automatic multimeter, a true RMS multimeter. So that's exactly one of those features that I wanted. So let's hope that this is good. Oh, this is fancy. This might be actually really useful for us, if I understand this correctly, that you can put it up on here like this, and then you can plug in your components just in there to test them, plus minus and stuff like this. If I understand this correctly, that seems useful. Oh my gosh, look at that. Do the kids in chat still remember this kind of connector? This 8-bit computer runs some sort of emulation. No, it's like an 8-bit, it will be entirely in hardware implemented 8-bit computer. There's no emulation. It will have our own instruction set kind of stuff. Yeah. Let's get this out of here. Okay, does it have a battery? This is complicated. Oh, off. I'm an idiot. It says off here. I need to turn it on. Okay, let's do a test. Let's measure something. Let's see. Here I have a resistor here. Let's measure this resistor's value. Why is everything blinking? This is a first part, what will be later a whole like computer built on these things. Up here is a clock module, and these are other modules. I can explain all that in a second again. I would just want to finish like the unboxing stuff, and then I can again explain where it is. Or actually, wait, I added like commands what we are building here. Let's see. Did I add something? Ah, crap, I'm not sure if I added this. Parts. Okay, if you follow that link there, you come to the parts list, and there's also kind of an overview of this project. I'm following here Ben Eater's series on building an 8-bit computer on a breadboard here. And we are very slow with that. We mostly are chatting instead of building, so that's why we are in just chatting category, I guess. Okay, so let's see this multimeter. Okay, let's try the standard ones. These here quickly first. So if we want to measure ohm, so if you want to measure the resistor, we go in here. So I guess this doesn't fit for... so what do you measure with this? It does say R and C on there. This is quite dark. Oh, wait. It does say like R and C up here, so I thought that would be resistance and capacitance, but maybe capacitance, but maybe not, because this would go in here, and so, but over here it would measure. Oh well, over here would be resistance, but let's see. Okay, so let's put it up here. Okay, now it's not on off, but it's not turning on. Maybe it does need batteries. Do I need to screw this open? Quick starting guide. How fast is your computer? Right now it can go up to 500 hertz. 500 hertz. Here's also like with the resistor measuring thing. Wait, can you? Yeah, okay. I don't know. This we will figure it out. I might just look at it myself. We don't need to do this with chat. I just need to figure out if we need to put a battery in there. will it be in the top 500 supercomputers? It might be in the bottom 500 computers. Pressing red buttons is always a good idea. Yeah. Is that enough already, or do we need the... yeah, okay. Okay, no battery in there. What does it need? A 9-volt battery? Okay, so there's no 9-volt battery included. Or is it 9 volt? That should be 9 volt, right? Why does it not even say that on here? Does it say it on here? No, but of course it's 9 volt. I actually might have still one. Yeah, I still have one in here. Ah, that's perfect. I'm so prepared. I'm so prepared. I'm pretty sure there were slower ones. Yeah, but they don't exist anymore. So, or there are only a few left. So this one can join the bottom 500. Okay, plus goes in this way, and then we can. Wait. With the... Okay, well, whatever. Yeah, we are 42 minutes in and we have added 0 wires. Is that amazing? Well, we started with an unboxing, so there's that. Okay, let's try this again. Oh. I cannot build stuff. I'm too stupid to put this back together. There we go. I put it in wrong. I need a different screwdriver too. It's too small. That means you will have infinite progress after the first wire. It can only get better from here. Okay, there we go. Okay, let's try this. There we go, it turns on. Okay, so now we should be able to hold that against here. And we measure 150 ohms. Sorry. 150 ohms. You could hook Arduino to the multi... Right, it does have a serial connection actually. We could totally hook that up to the computer. That might be a fun project. Maybe, I'm sure we will reach a point where we need some parts or we need to wait on something. And that could be a fun project to write some code to be able to put that on stream. That would be actually pretty cool. Also, some people would say I should also try to hook the oscilloscope on the stream as well. On the other hand, we make so good progress, so we will be soon done with this. And then I don't know what we do afterwards, because it's not like I do a lot of electronics. I don't know what we do after that. How to change the battery of a multimeter? Yeah, fail. Okay. Now I would quickly want to check out this thing here. So how does this work? So I guess the only way to put it in so that it's still connected to ground here would be like this. Right? Like the only way, this is ground, but over here would be resistance. But on here, there's like a picture of like here's a picture of measuring resistance, that you could do it with these hooks, how we just did. This is the symbol of a resistor, just in case you didn't know. And then here it uses the thing plugged in, but it's like plugged in like over here. Does that make any sense? I love to see others struggle so much with hardware like I do. Yeah, this is a pure amateur stream. Don't expect anything. We are all here to learn something. Hopefully. Okay, I mean, what could go wrong, right? So let me plug this just in here for now, and let's see. Could it measure the resistance if I just like put it on there? Or put it in there? Of course not. What happens if I put it over here? Like that? Is that terrible? Will this blow up in my hand? No, okay, it does work over this. Oh, now I just noticed. No, they are both ground. If you check here, this is the symbol for grounded, for ground. And so I assume because these are connected, both of them are ground. So this acts as a ground and can thus also be used to measure resistance. So we can, that's pretty cool. So we can use that thing here. And if I have a resistor like this here with the feet, I can just like stick them in there, hold them there, and I can just get the measurement. That's awesome. That's a useful also multimeter. I am happy with this purchase so far. Cool. Awesome. Okay, now I have one last thing. One last thing arrived, and I hope this time it's better. Who can guess what else we have? What else is in this smiley box? Ground is common. The connection means they are sharing common ground. Okay. Fail. Whatever. Everyone from last week knows. Let's really hope this one is better than the terrible thing we had last time. A CD! Just kidding. A wire stripper! Please work for our purpose, please. Oh, please work. This one is massive. An ancient artifact. Oh my gosh. Oh my gosh. I can't believe it arrived. You have an old wire stripper and it says made in West Germany on it. Yeah, some old products still can have that. Mine was only like 30 years now ago. Start lifting weights, man. This is quite heavy, I can tell you. Okay, let's see. I haven't changed any of these settings. So, how would I adjust? Down here. Okay, so this wheel down here clearly moves the height of these plates there. So, okay, let's try this. Okay, so this was way too far apart. Oh my gosh, this is incredible. See that? Wait, let me put that here. See this ancient technology? Bam! Beautiful. My gosh. It works! It works! At the top I can cut the wire too. Up here. That's... Oh my gosh. Okay, this thing, if you do shortcuts, it might get trapped in there. That's maybe not a good design. Okay, but yeah, awesome. You can see I'm so relieved, finally. Time to strip all the wires. Yeah, let's just strip wires. Let's not even continue with building. Oh my gosh. Oh my gosh, I'm so happy. Okay, let me just... I'm sorry for everybody on stream who... I'm constantly explaining always what we do. Just a very quick rundown, and then we head into the first video, which will be a bit boring anyway. Because we will continue Ben Eater's series, and I believe he does like troubleshooting stuff. It will be just like YouTube videos that we will do, and then we will have a reaction stream basically. Okay, so up here, this whole thing is supposed to be a whole computer, like mostly the CPU, and then obviously there's also some RAM that the CPU uses to, as memory. And so what we are building here right now are different modules that all together build this CPU, this computer. And so we started up here with the clock module. So this is your clock of the CPU. Your modern CPUs run with 3 or 4 gigahertz or something. This clock module right now can run with up to 500 hertz. So 500 times per second clock cycle. Right now even slower because you can see the clock blinking. We can adjust the speed here, so to make it really slow, and then you can really observe, how the data is and how the bits are moving inside of the CPU around. That's the cool thing, right? It's a CPU with the different blocks. What is usually on a big chip and you can't look inside, you see it here spread out and you can see it. We have also here a switch that we can change, and now we can have a manual clock. So as you can see, we can manually issue clock cycles and let the CPU execute it manually. So this is great, so we can again observe how the CPU is internally working. And then these two things here, these two modules, they look very similar as you can see. They all have these 3 chips and then some blue and green wire there. These are 2 registers. So each CPU has a couple of registers that are used for various things during execution. Your modern CPU has, your modern x86 Intel CPU that you have has I don't know how many registers. There are also special purpose registers for floating point calculations. You have a register that's just for flags. So you have a couple of different registers. I would say maybe 16 normal ones, maybe something like that. So this CPU so far has 2 registers. There will be a third one, I believe, the instruction register that holds the address of the next instruction to execute. But yeah, so this CPU is very limited, has only 2. These 2 registers are connected through an ALU, the arithmetic logic unit, and these are the chips here. So this module can do arithmetics. In our case, it can do addition and subtraction. So also not very fancy, no multiplication, no division, nothing fancy, just adding and subtracting. And this is implemented on these chips there. And so far we have that. And then these components will later be combined with a bus. So if you have ever heard about a CPU bus, a memory bus or something like this, this is that multiple components are connected to these shared wires, and then they can read and write to and from that bus. That bus is literally like a network. You can almost imagine it like the internet, not connected computers, but connected hardware pieces here. And yeah, and there will be other components. I believe the next module that we will actually build will be the RAM, so the memory, and this is our current state. And so what you see right now here, this register is configured to read from the bus. The ALU is configured to write its result of the addition onto the bus. So with each clock cycle, there will be an addition happening, and the result will be loaded back into this register, which will then be used in the next addition, and then so it goes around in a circle with each clock tick, and that's why with each clock tick you see here the binary number changing. If you have passed like 5th grade or something in school, or 6th grade, you might have also had binary numbers in math. So what you see here is just binary numbers, zeros and ones, and it's performing a subtraction right now, constantly decrementing. Okay, so that was that for the summary. And thanks for the bits, Mokiros. All right. Okay, so what did I promise we do next? I said next we watch the video, right? Yeah. I'm not even sure it could ray trace because so this computer version will also have 16 bytes only. We need to extend it to have more than 16 bytes. Okay, so again, this is based on Ben Eder's series on building an 8-bit breadboard computer. We are following along his series. The next video in this line is troubleshooting the ALU, because Ben Eder, I think, has some issue. I believe we don't have an issue, but we will still watch it because we will learn how you can debug and find a mistake you made, an issue that you have with your hardware. So I'm sure it will be interesting regardless. 16 bytes for image. These 16 bytes have to also contain your code. So you need, that is memory that shares instructions and whatever you need for variables. Okay, let's start with that video then.
So in the last video, we built this arithmetic logic unit, which is this circuit here, and it's designed to add or subtract the values from the A register and B register. And when we connected the power at the end of the last video, I noticed right away that it doesn't look like it's working totally correctly, right? Because when it powered up, we had a 0 in the A register and an 8 in the B register, which is fine. The registers might power on with any value in them. But what I would expect to see is that 0 plus 8 is equal to 8. And instead, what we're seeing here is a 4. And then when I switched from adding to subtracting, I'd expect to see a negative 8, which is, I think it's 5 zeros followed by 3 ones. And I'm seeing something different. So something's not working right about this, which, you know, frankly happens probably the majority of the time when you build something new. And I thought rather than trying to find it myself and just like swapping a cable or something, whatever it is that fixes this, and then editing that in at the end, I'd actually go through with you kind of my thought process and how I troubleshoot this. So since the last video, I haven't looked into this at all. I don't really know anything more than you do about what's working or what's not working. So I guess the first approach that I would take with this is just try to simplify things and just understand, you know, what behavior the thing is exhibiting, and then try to narrow in on what's going on. So, you know, right off the top, it looks like maybe there's a bit swapped around. So instead of the fourth bit, you know, it ends up as the third bit. So, you know, there's this connection over here, and then the connection over here, maybe something got swapped. But then the negating, you know, I'd expect to see something a little bit different there. So it's not super clear that that's the issue. So what I'm thinking as a place to start is just try and you know, set both of these to 0. So I'm going to clear this. So that cleared the B register. And so now with the A register and B register is 0, the output is 0. So that's good. That's a good sign that 0 plus 0 equals 0. Now we can try, okay, good. 0 minus 0 is also 0. So that's what we'd expect to see. So now we could try some different values here. And you know, my thought process here of just testing this, because I guess the first thing I want to do is just test it in different ways to see if I can isolate parts of the circuit that are working correctly, or maybe parts of it that aren't working correctly. So my first thought is, the simplest part of this was one of the early parts that we built, which is connecting the A register to the adder. So if we've got 0 in the B register, then whatever's in the A register ought to show up in the output. So what I can do is, put some value here in the A register. Remember what all these things are. So this should load the A register. Okay, so we loaded a 1 into the A register, and we see a 1 in the output. So 1 plus 0 is 1, so that's good. And I'm just going to try each bit. I think that's going to be the easiest. Okay, so the second bit is connected through. And just try the third bit. So that's connected through as well. So we're just seeing, this is 4 plus 0 is equal to 4. And let's try the next bit. Okay, yep, next bit works. So we're just keeping the B register at 0, and we're just trying different values in the A register to see that it is connected correctly, because a very easy way to get this wrong is just if we've swapped our bits or something in here. Oh, so that's interesting. So here we have what is a 64 in the A register plus 0. We'd expect to get a 64 here, but we're not. So there might be an issue with this bit. So let's try to trace this wire here, right? Because this should be on. And actually, I'm going to get a multimeter over here. Yeah, it's as nice as it is having all these LEDs everywhere. Sometimes just measuring voltages can be
Look
can
at
be really
that
helpful.
expensive
So I've
Fluke
got,
multimeter.
multimeter here, and then the probes are just these little clip probes that I have these wires attached to. So I can just hook my ground over here somewhere, just connect it to my ground, and then I can probe around with this and see what we've got. So go over here to volts. And so the LED should be connected to this pin here. And yeah, we're seeing some voltage there. And then that should come down here. If we follow this wire around, looks like it's going to this pin here. And that pin is, so A3, so it's one of the inputs here. And then the output should be coming from some, what is this, pin 13, which is our output 3. And that ought to be going around here somewhere. And I'm not sure I see, I'm going to zoom in here because I see this connection here. This is the input for this bit. And I believe it's coming around, it goes under here, and then here into, this is pin 14 on this adder. So pin 14 is bring this in. Pin 14 is the A side of our bit 3. So we have A and B, so A and B, and so it's going to add them and give us an output here. So that looks okay, but what I'm not seeing is the output here on pin 13. So pin 13 is right here, and I'm not sure I see anything connected to it. What should be connected to it is this, which of course is underneath everything. And it looks like it goes, wow, where is this going? Is that going to 4? Oh, are these backwards? No. What is going on here? Ah, okay. I think I see it. It's kind of hard to see here, but let me see if I can trace this through here. So this is, yeah, so we should have this bit here, the 64 place, or the, this bit is connected here, and it comes in over here, and that part looks fine. The output of that bit of the adder is here. And what it looks like is that I've got it off by one spot. So this wire right here, you can see it going down here into this pin here, should be over on this pin, because this pin is supposed to be the output. And that wire, if we trace it around, goes underneath a couple other wires, but I believe that it comes around and is this here, it's this pin. So I believe if I find that wire here, which is this one, and I just move it left one place here to this, and there we go. And now that output looks good there. So hopefully that is one problem. I suspect it is not the only problem though. So let me zoom back out, and I'm gonna retry all this stuff just to make sure we didn't mess anything up. So got the first bit, second bit, third bit, fourth bit, fifth bit, sixth bit, and then the seventh bit, which we just fixed, and then the eighth bit. Nice. Okay, so we found and fixed one problem here with our A register connecting to the adders. I suspect there is still another problem with the B register, because you remember when we started out, the A register was 0, so we wouldn't have encountered this particular problem. So now we can try the same thing with the B register. So I will change it so that our B register is loading data from the bus, and then I can manipulate the value on the bus over here to load into the B register. Oops, nope, that's our subtract bit. This is the B register load. There we go. So again, now instead of a number plus 0, we're doing 0 plus some number in the B register, and we can see if we can figure out if the B register is hooked up properly. So that's our first bit. Our second bit looks good. Third bit is off, and this is, okay, interesting. This is almost what we saw earlier. I think earlier we saw when we had the fourth bit. So we're somewhere we've swapped the third and fourth bit. So yeah, if you look down here, when we've got the third bit on here, we get the fourth bit on over here. So it's saying 0 plus 4 equals 8, and then if we have our fourth bit on down here, then it's saying 0 plus 8 is 4. So I think we've just swapped those two bits somewhere. Now it could be here in the connection from these bits down here to the XOR gates, or it could be from the XOR gates to the adders. It actually probably doesn't matter. Well, we probably screwed up one of them, but we could probably swap it back on either of those, as long as we have it swapped the right way around. But let's keep testing, see if we have anything else swapped while we're here. Okay, so the fifth bit looks okay. The sixth bit looks okay. Seventh bit looks okay, and the eighth bit looks okay. So it looks like we just swapped these two. So, oh boy, we have all this rat's nest. So let's see. I guess it probably doesn't matter where we screwed this up, as long as we fix it somewhere. So maybe it's easiest just down here to swap these two wires. So let me zoom in. Yeah, so this is the B register down here, and you can see these wires that kind of go up here are going up to our XOR gates, which is part of our negation logic that goes into our adders here. So I think the easiest thing to do is probably just down here, where we have our third and fourth bits connected up to here, just to swap these two wires. So I'm going to pull them both out. Well, I'm going to pull that one out, and then we'll just slide this one over to the left, and then put this one back in over here on the right. Come on. Here we go. And so we just swapped those two, so hopefully that will, or well, I mean, I don't know why I wouldn't. That should fix what we're seeing. So if we zoom out here, So now we can try again and just see that all of these line up. So
I've done the same
look at
test
our
right now,
first bit,
and it
second
looks all
bit,
good on ours.
third bit.
So we
fourth
don't have the
bit.
same mistake.
Nice, they are in order. And fifth bit, oh, there it is. Sixth bit, seventh bit, and eighth bit. Okay, so now I'm reasonably convinced that we've got all of our bits in order, which is pretty good because all this mess here is. So now we could try maybe a couple other things. So one thing we can try is just some simple arithmetic. So we can load maybe a 2 into here, and then let's load. There we go. Whoops. Stop loading. Okay, so we've got a 6 in the A and then a 2 in the B. So 6 plus 2 is equal to 8. That's good. And if we turn on subtract, we get 6 minus 2 is equal to 4. So that looks pretty good. So that actually wasn't too bad. I wasn't too sure what problems we'd encounter, but it looks like we've probably found most of the problems. So it looked like it was just we had one connection here that was just plugged it in the wrong place, which is obviously an easy mistake to make. And the other was we
I will explain in a
here,
second, Stashu. You will see
swapped,
again.
which is also an easy mistake to make. And I think it's pretty common that something, certainly something complex like this, the first time you build it, it's not going to work the way that you expect. And an important part of engineering, maybe the most important part, is having the sort of persistence or tenacity to take a step back and kind of work through and sort of systematically try to figure out what is or isn't working. Because at first it was like, well, it's adding these numbers wrong, what's going on? But thinking through, okay, well, let's try the simplest case of 0 plus 0. And we got 0, which was good. We might not have. That would have been interesting. And we could try our subtraction. We could see that 0 minus 0 was also 0. And then working through each bit. And that, maybe required a little bit of intuition of what the problem might be, or a little bit of, maybe that came from some of my experience just knowing that, an easy thing to screw up here is getting, some bits mixed up, or if one wire was off, then it would affect one bit. And so just, methodically going through each bit on each register and making sure that we got the expected result. And it's important to have a way of troubleshooting things that's methodical and where each thing you're doing gets you a step closer to better understanding what's going on.
All right. Okay. So
well, now that we've built
we don't have the same issue, but we kind of knew this already from last stream. I think it's so cool that now people are stumbling in here that didn't come like from my YouTube or something and have no clue what they are seeing. That is awesome, because that is kind of what I was hoping by streaming and just chatting. To have people come here, and maybe a lot of people might find it boring or not interesting, but maybe there are a couple of people who think, hey, that's actually cool, I want to check this kind of stuff out in my free time as well. So that would be awesome. But yeah, we are following here a YouTube series by Ben Eder, who has built an 8-bit computer on these kind of breadboards. So these are prototyping boards. And we have implemented a couple of the modules already. And Ben Eder, when he was building it, he did a mistake. And so we watched his troubleshooting video about he connected some wires wrongly, and then this circuit here is supposed to perform a binary addition, and it wasn't working correctly for him. So this was his troubleshooting video. But when we built this yesterday, we connected the wires correctly. We looked also in the data sheet and made sure we connected correctly, so we didn't run into the same error. Right, so this is what you can see here. Oh, I forgot to switch the camera view. So I've also here in my setup various camera views, so you can follow along building, and we can watch the videos and continue doing this kind of stuff. And along this, we are also chatting a lot, because I make very slow progress while streaming. But yeah, look at this here. I've played around with this while we were watching the video a bit more. So I have connected here these to the clock signal right now, and so this can also measure the hertz. Last time we had to use the oscilloscope that is up here to measure the frequency of the CPU clock, but we can also measure it here. So right now it's running with 2 Hertz. And so we can also increase the clock speed of the CPU, and this multimeter can also display this. So 5 Hertz, 15 Hertz, 122 Hertz, and then we can also go all the way up to 0.5 kilohertz, so 500 Hertz. That's pretty cool. In terms of review of the hooks that I bought, I'm actually not quite happy. They are actually bigger than I thought they are. If you look here on the Canon camera, you see that they are quite thick. So if you want to plug them, like hook them up while they are sticking into the breadboard, they lift the cable up quite a bit. I was hoping actually to be a thin kind of wire. It's a bit too thick for this kind of breadboard work, so maybe I need to find some others. But yeah, that's still pretty cool. All right, let's remove that again. There we go. Okay. Why don't you use Firefox? Why should I use Firefox? Or at least Chromium? Why should I use Chromium? Micro test equipment. That from the name sounds like it. Oh yeah, these look good. Yeah, that sounds good. I might order these. I just did a Reichelt order. Next time. What has been happening so far? Since when? Since the beginning or since now? Gosh damn, we are building this, but so far nothing really happened. We watched the video of Ben Eder troubleshooting the ALU. The next video is testing the computer's ALU, but we also kind of have tested it already. We did this incrementation loop, so we have seen it working already, but it's also only a 5-minute video, so let's get that over with, I would say. Since the beginning of the stream, unboxing, pretty much only unboxing. And we got a cable stripper now. It finally arrived, and it actually works. Did your setup have... No, my setup didn't have the issue because we were not blindly following what he was doing in the videos. So I also always had the schematics of the chips open, so I knew which pin has to be connected to what, and I was connecting it based on that. And so if I had just blindly followed what he was doing in the video and always paused, then I would have had the same mistake. But because we always looked it up ourselves, we just didn't make a mistake there. Broken enough for a 3 a.m.-ish appearance on a podcast tomorrow? Yeah, I could make that work. Okay, yeah, let's watch the next video.
Arithmetic and logic unit, our ALU, and we've got it working, so it can add and subtract. So right now it's got this is 6 minus 2 is equal to 4, and we can also add. So 6 plus 2 is equal to 8. So we can add and subtract. Now what we can do is hook it up to our bus so that we can take the output of...
Xele, do you mean 3:30 a.m. like tomorrow, like in like 6 hours? Or do you mean tomorrow in like 30 hours?
Of the arithmetic and feed it in.
I could do either way though.
So what I'm going to do is I guess first disconnect my bus from any kind of external input here, and then I'm going to actually just disconnect the instruction register here. We're not using that
let's
right
do
now. So rather than just adding more mess to this, I'll just disconnect it and use these same wires. And so being careful to keep this stuff in order, I'll hook up all 8 bits here.
We did that too, by the way.
And so now our bus is connected to the ALU.
You can see here.
Of course, this is only used for output from the ALU to the bus, right? Because the ALU gets its inputs from the registers. So the inputs to the ALU, you have to load them into either the A register or the B register, actually both the A register and the B register, and then it will either add or subtract them, and then just the output goes out to the bus here. So we can use this, ALU output, or EO signal. If we take that low, then whatever's in the ALU, in this case it's an 8, goes out on the bus. Now, what we can do then is read from the bus into the A register. And what's kind of interesting here, I'm going to stop the clock. And I'm going to, so with the clock not running, if I enable the A register to read from the bus, nothing happens, right? Because it's not until the clock goes high that we'll read from the bus. But something interesting is going to happen here, which is really important to understand the nuance here, because remember the A register, or any of these registers, is going to read on the rising edge of the clock. And that's really important here because on the rising edge of the clock, the value on the bus is an 8. So it's going to read that 8 on the rising edge of the bus into the A register. But as soon as that shows up in the A register, then this value, this 8 that's going out on the bus, is going to change, because instead of taking 6 plus 2 to get 8, it's going to be 8 plus 2, and this will turn into a 10. So as soon as it reads this 8, immediately the ALU is going to keep trying to add these two, and it's going to give us a 10 here. And the ALU is outputting to the bus, so there's going to be a 10 on the bus. So then you would think that the A register is going to read it in again. But because we have the clock, and this is the importance of having that clock in there, it's only going to read, just that instant when at the rising edge of the clock. So when I push this clock, you see just at the rising edge, it just reads in the 8, and it doesn't then continue to read in the 10, even though this changed almost instantaneously. And I think that's the key, is that it's almost instantaneous. So it's able to read in that 8. And then the next clock, it's going to read in the 10. And now there's a 12 on the bus. And next clock, it reads in the 12. The next clock, and now we have a 14 on the bus. The next clock, it'll read in that 14. And now we have a 16 on the bus. And so you can see each time the clock goes, it's adding 2. And that makes sense, because we have a 2 down here in the B register. And so every time we put a new value into the A register, we're adding 2 to it and putting that into the ALU. And then that's being output on the bus. And so then the next clock, we bring that into the A register. So if we just let the clock run, you see at every clock's pulse, the A register increments by 2, or we add 2 to it, because we have a 2 down here in the B register. And so you can see it's just counting. And we can speed the clock up if we want to go faster. That's a little bit too fast to see, but there we go. And so you can see it's actually just counting by 2s with each clock pulse. Of course, in addition to adding, we can also subtract. We can set our add and subtract bit to subtract. And now it's actually subtracting 2 each time. 0, and then it wraps around, and it subtracts 2 each time. And so I think that pretty much does it for our ALU. So we've got our A register, and we have our A out and A in signals that we can bring high or low to turn on the A in or A out signal to read or write from the A bus. We also have a clear signal here if we want to just clear it. And then we have our B register with the B out and B in signals that we can set, and then of course a way to clear the B register. And then we have our ALU, which has an out signal, which outputs the contents to the bus. And then we also have this add or subtract bit, which we can add or subtract. And so that pretty much does it. We've got our 2 registers, and we've got our ALU, so we can put some values in here and do some math. I think in the next set of videos, I'll focus on memory, because we want to be able to have some memory that can store different values, so we can read those in as well. And then in future videos, we'll talk about the control logic, which actually will automatically control all of these different signals that I've been doing manually. So in a previous video,
cool.
We made this 1-bit register, and it's got...
Okay, so I just want to show you again. We are taking notes. Wait, what? Oh, Block Lab, thanks for the Twitch Prime sub. He just went away. Why is nobody writing in chat? We are taking notes. I'm focusing. It's complicated stuff. We all need to be concentrated. Okay, so let me show you, for the people who arrived later in the stream, something cool that also arrived today. let me demo something. So right now, what I was just doing while this video was playing, I have brought in like this. You see that hose there? So I have an AC unit in the other room, but I can't run the AC unit in here because it would be too loud for the stream. So I've added this like hose. It's like a 10-meter hose. So it reaches in here, so I get a bit of fresh air in here. And so this is cooling down the chips right now a little bit here. Here, cool the chips there. Because I wanted to demo the thermal camera again, because I paid money for this, and so we need to use it every couple of minutes so that it's worth it. So yeah, we got a crap. That's how it works. We got a flared thermal camera that we can hook up here to the phone, and we can display the image of the phone on stream as well. So let me plug that in. So we can look at those of the temperature of these chips here. So you can tell that they are already a bit warmer. So this was obviously running for a little bit. So that's why in generally they are here a bit warmer. Even pointing now the output of this exhaust and there, it doesn't significantly lower it. However, the temperature difference is, I don't know, not that high. What is it, like 28, 30, 34 to what temperatures is like over here? 29. Yeah, okay, still has a little bit of a temperature there. But we can change the scale here just so that we notice it a bit better. And let's go down here to like 24 or something. So, oh no. Oh no. FLIR camera, what are you doing? Why are you letting me down right now this moment? There we go. We are back. This, I cannot believe how expensive this device is and how terrible it works. Absolutely awful. Okay, anyway. So let me turn on the electricity again of the circuit and let it blink again. And then you should notice, we should see the chips getting even hotter and glowing. You can already see them start glowing. Do you see how they even start like more glowing on the left side than on the right side there? That was quite interesting. So let's increase the clock a bit. But yeah, you can clearly notice how they get more yellow and more yellow, the chips itself. So you can see that these chips are heating up. They are actually not warm to the touch right now. So they are actually, it's not like bad or anything. But the camera, because it's I guess so sensitive in that case, can still notice the difference. How well does it work on my body? Well, see, you can do like cool stuff like this. Like I can touch here, and there's my handprint. Isn't that cool? What a toy. What a toy. Well, the hope is that we can like see if we have like overheating components because we connected them wrong, that we would be able to see that and see them like spiking up extremely. Like right now these chips are just like 44 degrees and this in this room is already pretty warm. So that's like perfectly fine. But if it would get up to 50, 60 or 70 degree, we would know, oh crap, this chip has a problem. And so we can use that for debugging. At least that's what I tell myself and how I justify the cost. It's like 380 euros or so. Okay, you want to see my face? Are you ready to see my face with that? Scary. the power supply there too, and up there you can see the cold air rushing in. I mean, it's not that cold, it's like, you know, not that efficient. 24 degrees is coming in there. Yeah, pretty cool toy, huh? But you can also see that, for example, the 555 chips up here, so these clock chips, they don't really get hot. It's really these ones that are driving also, like these output LEDs and stuff like this. I guess that's the reason why they get hot, so hot in difference. And also, it's interesting that it gets hot over there. Why does it get hot over there? So this is the... it's not quite clear which cable it is that is radiating this heat. Oh yeah, no. These are the wires coming from the power supply. I guess maybe this connection... I mean, this is drawing like 0.6 ampere right now. And maybe these wires are so thin that they just do heat up a little bit. I mean, again, not massively. Like, they are not burning through or anything. It's just like 2 or 3 degrees hotter. But you can still clearly see that. On the other hand, these wires here are pretty, yeah. You can also adjust here. The camera alignment is a little bit off. It depends a bit on the angle and stuff. So, no, it's kind of there correct. Yeah, isn't that cool? The resistance in those contacts there. Yeah, it's kind of, you know, it's just interesting that it's from the, but I guess logical, because here's the most current flowing through this, because you don't see it really on the other power distribution wires, but only the one that is coming from the main power supply there. Neat, huh? All right. I wonder if it interpolates the IR data with actual RBG camera. Yeah, so as the FLIR camera has 2 cameras on there, and so what they are doing is they are overlaying it. They call it MXR or something like this. It's a feature of FLIR. Other cameras have higher thermal resolution than FLIR, but FLIR has this overlay feature, which makes it look very nice. And yeah, so they do like some edge detection or something and overlay it. Nothing really fancy. I wonder why the other manufacturers are not really doing that. Maybe there's like an annoying patent on it. Was the camera more expensive than the phone? That might actually be true. It's the Pixel 3a. I forgot what it cost, but it's like the cheap Pixel phone. So it might, was it 350 or might have been 400 too? Around the same price, I think. Okay. This is way too useful for pin reading attack using the radiation of the used buttons. You know, the US government determines a lot of these things as, classifies them as weapons. That's why they have so low frames per second and stuff like that. Are there enough decoupling caps? We have only one up here right now in the corner there. That's all so far. But so far we haven't seen any issues. Once we add more modules and we build the bus and everything, I definitely want to improve the power supply. I want to put proper wires around the border and solder pins on that main wire so that each component gets the proper power from the power supply. Yeah. Glue the pins, yeah. You know what? When the first time I did like electronics as a teenager, I was modding my... Maybe I can even find the video or some pictures of it. Oh, in some YouTube video, I might have even shown a short clip of that. So I modded my school's calculator. Like we got my camera. We got these big graphing calculators in school. You know, like the bigger ones. So I cut like a window in the back so you could see the PCB of the calculator, and then put plexiglass in there. It was completely scuffed and dodged. It looked terrible. But then I put like LEDs in there and hooked it up to the battery of the calculator as well, and added a little switch. And so when it was like put down, you could turn it on, and then it had like underground lighting, like, you know, like cool cars just on a calculator. And then if you turn it over, you had like the window, and you could see like blue LEDs on the onto the PCB of the calculator. And I didn't have a soldering iron back then. I did that all with a hot glue gun. Hot glue gun, and just like drilling the wires around the legs of stuff. There's like one YouTube video where I show that, maybe the how to learn hacking video or something like this. Maybe I included a short clip of that actually. But yeah. Was it the TI Inspire? No, we had Casios in our school. I was actually super jealous of the people that had the TI, because the TIs, they look cool and sleek. They were like black and boxy. The Casios were like wavy and white and purple, so they didn't look as cool. Do you have a scope? Yeah, I have a scope there. You can put the multimeter on AC and measure the supply next to an IC. Ideally, it should show 0. The more it shows, the more noise it's on the supply lines. Yeah, we could do that at some point, I guess. Do you want to see it right now? Did you graduate in electronics? No, I do computer science, so mainly I do software stuff. Right now, this is absolute amateur stuff I'm doing right now. I couldn't build this myself. I'm following, the video series, right? I'm an amateur in electronics, but I like to learn that. That's why I'm doing it. Do you have a home lab, like servers and stuff? Not really. I have like a NAS, and I have like a little Intel NUC with that I but basically not use. That's all. Yeah. So I have probably a better electronics home lab than like a server lab, but I don't really need servers or anything. Every time when I need a machine, I usually rent it from like DigitalOcean or something. I don't remember the Casio model anymore. I'm not sure if it was the FXCG20 or whatever. Okay, now we are getting in the computer RAM. That's another 13-minute video. Did you participate in the CSCG? No, I'm now too old. I'm now too old, but I did participate in some previous years. The camera moved. Did I shake it? I kicked the table or something. The camera is cut off. Oh, how did that happen? RAM, bit more like cache. I mean, what's the difference? It's just like, Oh, there's a big difference. This is clearly RAM. I don't know. What's the recommended amount of dedicated RAM for an 8-bit CPU? I mean, ideally you have 256 bytes, but we only will have 16. When I put my drink down, I clicked. Oh, that's crazy. Can you give a sneak peek into the current status of your browser exploitation series? What do you mean? Sneak peek is look at Linus's exploit. We walk through that. Do you really think age is a criteria for learning a new thing? Not necessarily. If you're curious, you learn new stuff. I don't know if... I mean, I guess science tells us that it gets a bit slower with age, but then you just need twice as long. Who cares? Sleepless. I never used Skillshare, so no clue. Okay, let's start watching that video here. So the 8-bit computer RAM.
Got a single input, single output here. So in a previous video, we made this 1-bit register, and it's got a single input,
I'm 28.
single output here is the LED, and it stores 1 bit of data. And just as kind of a reminder, basically the interface for this is we've got our input, our output, we've got a write signal, which if this is active, then it stores whatever's coming in our input. And we have an enable signal, which when this is active, it sends whatever bit is stored in here to our output. And of course, the registers we've been building also have a clock signal, which for this video I'm going to kind of sidestep, but just as a reminder, you know, the clock makes this a synchronous register because it even if or when the write signal is active, it still only reads data on the rising edge of the clock. So it's synchronous in the sense that it's synchronized with this clock for when it's storing data. But for now, just to simplify things, I'm not including the clock here. We'll come back to that in a future video. We talk more about the actual implementation of our memory. Now, of course, after we implemented a 1-bit register, we then went on to implement an 8-bit register, which, you know, we've got a couple of them here. We've got, you know, this is our A register, this is our B register down here. And it's the same idea. It stores 8 bits of data instead of 1 bit, but we still have our enable signal, we still have our write signal, and then, of course, we have our clock in here as well, which is this white wire. And in this case, input and out.
Crap! We forgot to put a nice white wire underneath all the thick layers of green cables, like Ben Eater did it. God damn it. Maybe we can still squeeze it under there. They are quite high up. And then we can use maybe the wire strip for the first time. Let's actually do this really quick. I kind of want to do that really quick. Let's try that. We need to get this wire counter up. We are still at 0. We are still at 0. This is terrible. Time to disassemble. We are up to negative 16 wires. Yeah, no, I'm not ripping those out. Either I put the wire over it, yeah, I try to put it under or I put it over it, but I won't pull out those green wires anymore. So basically we want to go from like there. So that should be enough for us to play with. Yeah. Wow, we had 200 viewers. That's crazy. Let's turn it maybe off. Okay, let's see. How do I do this? Because we also need to bend it and stuff. Okay, let's strip one side. Let's strip one side of this for now. You don't even understand how simple that is. It's so smooth. Why do you cut wires for a breadboard? What do you mean? We need to cut wires. We need wires, so we need to cut wires. Okay, so if I put this in here, we need to 1, 2, like 2 over. So we need to bend like here. Okay, these are so nicer to bend. I still don't like this thing. I will look for a different pair. Do some wire stripping ASMR. Oh yeah, I should do that. Okay, like this. Okay, let's try to, I guess. Come on. Wait, I can try to show this here on the other camera. I did it behind the face cam. Ah, crap, I'm sorry. Okay, we can actually kind of lift that up. Let me get, I guess, this. We got through there. Now we need to, we can put that in there. There we go. It's a bit curved now, just because of, actually maybe, can we bend it in place here maybe? That actually seems to work, kinda. Okay, now it's further over there. This camera here has nice colors. This one here. I've also forgot to put the light up here again. I need to get a light without rechargeable batteries. We are running to like 2 pairs of these batteries at least per stream. I'm constantly putting them back. I've never recharged these kind of AA batteries so much in my life. Okay. Yeah, that one. Yeah, I guess here you can see the difference between a Logitech webcam and a proper DSLR. However, I did color correction on the Canon, and I don't think I did that on the Logitech. So the Canon is, you know, shooting with in a certain color preset, and then like in a, you know, same thing with this camera. I also, you know, this is also a good DSLR camera, and I'm also running, you know, like a color adjustment, what's it called? Forgot the term. If you color code the cables, well, the cables are color coded. I mean, somewhat. So white is the clock. Yellow is the control lines. So up here, this yellow is, for example, the input enable, or here, this yellow is the controlling of subtraction or addition. So yellow is like control line. Red is VCC. Black is ground. Green is output of something, and blue is input. I think it was. So here, blue input is coming into these chips, and green output is coming out, and that output just happens to go somewhere else, and then that output also is not going somewhere else. This green output goes into here, and this green output goes into here, and later we will probably have different kind of colors to go onto the bus. Maybe, I don't know. The wires between IC pins. Color correction, like putting up a bit of saturation and different kind of color curve, just to make it like look a bit nicer. And not that I put like a lot of effort in it, but just adjusting it a little bit already makes a big difference. Put a label on the jump wires used to read-write app, because otherwise when you will need to wire them for opcodes, it will be a pain. That makes sense. I mean, for now, I still actually remember all of them, but that might actually be a good idea that we should do that. The green is called data bus. Oh, yeah, I guess that we could definitely use that term for it. That makes sense. Okay, right, the clock. So we go up here. Oh, what we also need to do is arranging these LEDs, but this really sucks because they don't really fit there. This is really annoying. Really annoying. Hi, Pro GJ. Okay, so I guess we can bend this now here in place. And then, do I get in there with the wire stripper? So we need, this is getting crap. That might still kind of have worked. And then we put that, I feel like a surgeon right now. This is like really, okay, not 100% perfect, but absolutely good enough. Look in that camera here. I think that turned out quite well. And now, I guess for now we don't need to connect because this clock module will be later in the top left anyway. But we can remove this cable now. Let's quickly check if it still works. We put the input enable here. The output enable here. Input, oh, there we go. Okay, yeah, still works. The clock is arriving down there. That's what I want to check. What I'm working on now, nothing. I just added the clock here, the clock cable. Okay, so we can continue now. We fixed that. Hey, we added a wire.
Output are through the bus. So we have our 8 bits of input and output. So it's essentially the same idea as our single bit register, input, output, write, and enable, but now we've got 8 of them. So we have our 8 inputs, our 8 outputs. We have a write and an enable that either writes a whole byte into all of these, or enable, it outputs the whole byte from all of these. Now, if we want to build a memory for our computer, basically we can do the same thing and just replicate that 8-bit storage as many times as we want bytes that we want to store. So in our case, we're going to build a 16-byte memory. So we could essentially replicate 16 essentially registers, I guess, 8-bit register, 8-bit storage units. And we have a separate write signal for each of those registers. So write 0 will write into this first memory location. Write 1 will write into the second one. If this write 2 is active, it writes into the third one, and so on all the way up to write 15, which writes into the 16th byte down here. And you can see the 8 bits that make up the byte are connected to each of these, and we'd either have one of these enable signals active.
Yeah.
One of these 16 enable signals active, in which case we would be reading whichever byte is enabled. So if we have enable 1, that's this byte here, this row is enabled, then it would be outputting each of its bits onto each of our 8 bit lines. So these vertical lines, we can call those bit lines, and then these horizontal rows are essentially our words. Each one is a byte, but generally it's referred to as a word because it could be a different length depending on the memory. In our case, our memory is 8-bit words, but you could get memory that's 16-bit words or 32-bit words or so on. And so each of these memory cells, each of these little boxes here is a memory cell. And in our case, we're going to build these, or we're going to use something that's very similar to the registers that we used, which at its core is essentially a latch, which is able to store 1 bit of data. in practical memory that you might have in your computer, or for example the computer that I'm using to edit this video on, I have 16 gigabytes of memory in that computer. So that would be 16 billion of these rows essentially, which is a lot. I certainly wouldn't want to build it like this. But you can imagine, these flip-flops are fairly complex. I mean, you've seen the one that we built here. 16 billion bytes, that's 128 billion memory cells. So you wouldn't want to build 128 billion of these. That certainly wouldn't work very well. Of course, it can be miniaturized and all the rest, but even that is a fairly complex circuit to store one bit. So most memory, the memory in my computer that I'm editing this video on, for example, uses essentially the simplest way of storing a bit, which is essentially each of these cells is just a single transistor and a capacitor, and the bit is stored as a charge on the capacitor. Now, one drawback of that is that the capacitor will discharge over time. After a few seconds, it'll lose its charge, and so you can only store a bit in here for a couple seconds at most. But one way to get around that is to have a separate circuit that basically reads each byte of memory and then writes that same byte back into that same memory location. And so you have a separate circuit that's just doing that constantly. It's just going through all of memory, it's reading every byte, and then just writing the exact same data back to that byte. And so it's refreshing what's in each of those bits. So even though a capacitor could only store that data for at most a couple seconds, because we're reading and writing that many times a second, it's keeping that data refreshed. But because we have to continually refresh it like that, this is referred to as dynamic RAM. It's dynamic because if you don't refresh it, you lose the data that's in it. Whereas if we used a flip-flop circuit or something like we've been building with our registers, as you know, once you store a bit of data in here, it stays there essentially forever until we take the power away. So as long as this is powered up, we don't have to constantly refresh this or anything. We store the data in there, it stays there. And so this is, if we're using this type of memory cell, that's referred to as static RAM. And that's what we're going to do for our computer. And it's, static RAM is generally more expensive than dynamic RAM because you need a lot more transistors. There's a lot more complexity to each memory cell in static RAM. It has some advantages, right? You don't have to do the refresh, although that's fairly easy to do that, certainly in a larger scale computer. But it's also generally faster. So you see static RAM used in special applications where you need really fast memory access. Of course, we don't really care about speed for the computer we're building. We're basically using static RAM just because it's more convenient, because we don't want to have to build that refresh circuit. So for our computer, easy way to think of it is each of these bytes is essentially just like the registers that we've already built. So you already know how these work. The thing that's a little bit weird now is that we have a separate write signal for each of our 16 bytes of memory, and we have a separate enable signal for each of our 16 bytes of memory. And so that could get a little bit unwieldy. So what we'd like to do is be able to encode which of these 16 bytes we're reading or writing from using an address, because you can represent a number from 0 to 15 using just a 4-bit address. So the way we can do that is using this address decode logic, where we have 4 address signals, and these 4 bits essentially represent which address, which of the 16 bytes in memory we want to talk to. And our address decode logic starts out by basically giving us the address signals and then an inverted copy of the address signals. So we have A0 and inverse of A0, A1, inverse of A1, A2, inverse of A2, A3, inverse of A3. And then we just have a bunch of AND gates. And so if we AND together the inverses of A0, A1, A2, and A3, this AND gate will only turn on if all of these addresses are 0. So if it's 0, 0, 0, 0, then this AND gate turns on and our enable 0 comes on. And so that would be our enable 0. That would enable this first row in our address, in our memory. If we had 1, 0, 0, 0, so a binary of 1, then then this AND gate wouldn't be on, but this one would be, right? Because A0 is 1, and then the inverse of A1, A2, and A3 is also 1 because A1, A2, and A3 are zeros. So we have 1, 0, 0, 0. Then all of these signals are on, and so this AND gate turns on. And so now we're enabling reading from byte 1, which is our second byte here in memory, and so on. So enable 2 is 0, 1, 0, 0 is essentially what's coming in on our address lines over here. For 3, it's 1, 1, 0, 0, which is binary for 3. For 4, it's 0, 0, 1, 0, and so on, until we get down to our 16th byte, which is 15, because we're 0-based. And then in that case, if our address lines are 1, 1, 1, 1, then this last one comes on, we have enable 15, and that enables reading from our 15th row here. And of course, this is for our enables, and because we're also ANDing it with our enable signal down here at the bottom. And so we'd have something similar for the write lines as well. So we'd have all of these same things ANDed in kind of a similar way with our write signal down here instead of the enable signal. So this is essentially how we would go about building a 16-byte memory. Now, we could do this by hand and build 128 of these individual memory cells. But now that you kind of have an understanding of how it works, I'm actually going to use a chip that does this for us. And that's the 74LS189, which if you can't find that, you can also use the 74189 without the LS. For some reason, that one's easier to find, but if you can find the LS189, that's fine too. But this is a 64-bit random access memory. And of course, with 8 bits per byte and 16 bytes, that's 8 times 16 is 128 bits. And this is only 64-bit. And that's because it essentially has a 4-bit, it's 4 bits wide instead of 8 bits wide. But if we use 2 of these chips, then we'll be able to build our 8-bit 16-byte memory. And so if we take a look at the data sheet here, they have a block diagram on the back of what's going on here. And you can see they have a 16-word by 4-bit memory cell array. And that's basically what we have here. Of course, we have a 16-word by 8-bit. So they're basically just giving us half of this, which is fine because we can use 2 chips. And you can see they have the 4 bits coming in, they've got the 4 bits coming out, and there's a chip select and write enable signals that enable whether we're reading or writing from this. And then you can see the 4 address lines, and they just have this address decoder as a block. But of course, we just went through how that works. This is essentially what that address decoder is doing, or something very similar to this. And so if we look at the pinout here, just to get a sense of what's going on, you can see, like most of these chips, we've got our voltage and our ground to power the chip. But then we've also got our address lines, A0, A1, A2, and A3 are our address lines to select which of the rows we're going to be reading or writing from. And then we have our inputs, D1, D2, D3, and D4 are our inputs. So that's kind of coming in the top here. And then we have our outputs, O1, O2, O3, and O4. And something that's a little bit interesting here that we're going to have to account for is you'll notice that our outputs have a little bar over them. And that's because this chip, for whatever reason, the outputs give you the inverse of whatever's stored in that memory location. So we're going to have to end up putting these outputs through an inverter because we want to get the same value out that we stored. We don't want to get the inverse of the value out. So we're going to have to use some inverter chips to sort of or uninvert these, I guess. So we have our inputs, our outputs, our address lines, and then the only other pins on here are this CS, which is chip select, and that's essentially the enable. So whenever it's an inverse signal, so whenever it's low, it's active, which means that when that's low, then we're going to get data out of our outputs. So in our case, we'll just tie that low all the time, and then we'll use a tri-state buffer like we have for our other registers. And then write enable, and this is also in inverse logic. So when it's low, then it's reading in from our inputs and writing it to whatever location in memory is addressed from our address lines. And so that's the basics of how the 74LS189 works. And so in the next video, we'll wire this up and play around with it and start to build our RAM for our computer. In the last video, we looked at the 7.
Cool. This was actually the one chip that I had to order from eBay from China, because I also couldn't, as you mentioned in the video, it's somehow difficult to find them. Yeah, so. Why would a RAM chip output the inverted value? Yeah, I don't know. Doesn't really matter. Well, then just put an inverter behind it. You know, I don't know. You know, it's just as humans that think of it kind of as inverted, I guess. You know, that a 1 is a high and a 0 is a low is could also be the other way around. You know, this chip just happens to be so. It probably makes something on inside of the circuit a lot easier or cheaper or something. I don't know. But it doesn't really matter, you know. I bought mine used on eBay from Germany. Okay. Okay, I guess we can start with the next video. I definitely don't want to go too much longer, maybe like half an hour, so we can watch this, maybe even start like with, I'm sure he builds like a test module first. This building a RAM module has like 3 parts, so let's see what he's doing in the first part here. Usually with CMOS logic you have inverters everywhere because basic gates NAND and NOR, so undo the inversion you need an extra NOR. This is sometimes left out of the safe, out to safe parts. Oh yeah, makes sense. Dayum, you are still streaming? Well, I started like, oh, did you earlier go to the hairdresser? Was that you? Okay, let's head into the next video.
74 LS 189, which is the.
I like how I'm basically watching YouTube on Twitch. Yeah, you know, I'm one of these people without content, so I watch other people's YouTube video and do my non-reaction to it as content.
SRAM chip that we're going to use for the memory in our computer. And remember, it's gives us 16 4-bit words. And of course, we want 16 bytes or 16 8-bit words, so we're going to need to use 2 of these chips. So I've got 2 of these chips.
I'm so confused. Can we go back for a moment? Is the high speed 64? Oh, 64-bit. The whole time I've been thinking 64 byte, and I thought, why does he need 2? 64 bytes is so much more than 16 bytes. Like, why does he need 4? But 64-bit. That makes so much sense. So it's 8 bytes. Yeah, we did some unboxing. We got a wire stripper. We checked some thermal camera on stream. You know, we did a lot. And added 1 wire. We added 1 wire to our build as well. Please, let's not forget that wire.
I need to use 2 of these chips. So I've got 2 of these chips here. And then the other thing is that the output data is the complement of the stored. So it's got these inverters on the output, which we really kind of don't want. So we're going to have to re-invert those. So we're also going to use 2 of the 74 LS04 chips, which are these inverters. And each chip has 6 inverters. We're only going to use 4 of them from each chip. We'll start out by sticking these things on the board here. So we've got our 2 74 LS 189s and our 2 74 LS04 inverters. So now I'll just hook up power to each of these. And the last pin here is the 5-volt power, and then this pin 8 or pin 7 on these chips is ground. And so it's pin 7 on these chips because these are 14-pin chips instead of 16-pin chips. And I've got all these turns, so pin 1 is over here on the left. See the little dot there indicates pin 1. So we got the power hooked up for all of them.
Crap, I cut off my mic. Sorry. I was saying, what was the other chip? I missed it. But is that the inverter? Because it's like LS04. And 04 is such a small number that it seems it must be some of these very basic gates. LS. Yes, and for example, when you latch inverting, LS04, there we go. Okay.
So the first thing I'll hook up is the...
Check the orientation. I did. He has the nupsies at the bottom, and I have them here as well. Thanks for the reminder.
The 74 LS189. We've got the outputs here. Output 1, 2, 3, and 4. I'm going to hook these up to the inverters because these outputs are inverted and we want to re-invert them so that we get the right output here. So first thing I'm going to do is hook up those outputs.
Just let me see that I get the spacing correct. 2, 4. That. 4 in between. Like that. And 5 in between. Like that. The nupsies are at the bottom. Highly technical term there. Well, how do you call them instead? What do you call them? Aren't those nupsies to you? Holy crap, I just realized we have a wire stripper. This should be so easy now to do this. So let's cut a couple of black, 2 to 4. Some black wire. I call them dots. Why? But why would you call them dots? Are you ready? Oh, ASMR. That is the worst ASMR ever. To be honest, I did this before with the cutting the wire, and I listened back to it when I was editing it, and I thought actually that's a pretty cool sound. I'm looking forward to hear the wire cutter. The old one was better. Oh yeah, okay, yeah. So then maybe this one is better. Wait for it. That actually is better. Damn. Well, get used to this, because this is what you will hear more. I'm sure Wirecutter is a band name somewhere already. If I had this Wirecutter from the start, I tell you, we would already be done with this. Oh, I need to... How could I have lived without this? This is incredible. Why did nobody tell me to stop streaming until I have one? This is like torture. In retrospect. Oh my gosh. Can't use add wires. Yes, the problem is with that command, if I would allow everybody to do that, then we would get like double and stuff like this, so it should do one person. So I will just do it, just make sure to remind me if I forget. So we added 2 more. Because it's part of the evolution of playing with electronics. Sorry, I'm not sure what the response to was. Oh, it makes me appreciate this tool by having done it by hand for a while. Yeah, that's true. Oh, make me stop streaming without a wire cutter. That was the response to. All right. The emotions I feel right now, this is so great. Unbelievable. I also realized I need to change the add wire command to allow. I think it would only increment. I need to make a version where I can also just add multiples at a time. Otherwise, I need to always. So we got 1, 2, 3, 3 more. There we go. Do you want to add me? Do you have admin rights and you can just add it? Is that what you are saying? Are you hacking into my Stream Elements account to add this command? Nules is a real hacker. Pay attention. He actually can do this. I actually believe him that he can hack into my Stream Elements to do it. You all should be careful with him. Or her, I actually don't know. Okay, so what did he connect then next here?
And so that's the first, the 4 outputs of this first chip now are connected to 4 of the inverters on this first.
Okay, so to not blindly copy Ben Eater again, let's pull up the, oh, sorry. To not blindly copy how he attached the wires, we will look at the chip output again, just to be 100% sure. So first of all, to also learn how the chip like kind of looks like, but then also so we can make sure we don't make mistakes. We are in the RAM. So we have the inverter and the RAM. Where's my Club Mate? Nules, the add wire now, does it always expect now a number, or does it, if I leave it blank, it just increments once? I think I have a remove wire. I did it like, I called it my probably even remove wire. Moved wire. Why would we need moved wire? Oh crap, I think 26 minutes ago I missed a cheer by Pike.io. I'm sorry. Nules has forced you to accept free labor. No, he's employed. He's right here doing very good marketing for his company. Okay, so we connect, for example, the 0 with, and this is the inverter. Oh, so let's use this screen again. Okay, so do you use moved wire as a shortcut for remove wire and add wire? Ah, that's a good one. Okay, so we go from pin 4 here to the inverter here in the front, so we can like cut here. Okay. Cool. Oh, we were actually at 9 wires. Thanks, Nules. So here, this was proof that he was able to take control of my Stream Elements account and change the bot commands. And as you can tell, you saw my hands. I didn't do anything. Wasn't me. Thanks, Nules. That's useful. I want the graph with wires over time. Okay, I can endure a certain level of embarrassment, but we don't need to graph it as well. Here, Knowles, there you have your next feature request, built-in graphs for all the counts that you can have with the Stream Elements bot. Okay, so it goes from 4 to pin 1 over here. So that would be right here. I can actually cut a bit more off here. I can't get over this wire cutter. This is making me more happy than it maybe should. Like, of all the, I spent so much money for this whole stream the past few days. Basically every day I get some packages to just small stuff to improve my setup here. And this here is by far the one that makes me the most happy. Can you use it to cut wires as well? Yeah, there's a wire cutter up here as well. It's more like, still, I guess I have to force myself to not use this one. It's like habit at this point. After the millions of wires that I've already cut, it's like habit. Okay, so next one. Output. Frick. I connected the input, not the output. So it's 5 over here. A bit too long. Yeah, that's not a good one for something like that. Next year is building an x86 computer from scratch. Oh gosh, I think think about how many instructions that machine has. Holy crap. Just tuned in. One is working on. Yeah, we just started with the RAM. So this goes from 7. So from here to pin 3. So here. So we can cut like here. I feel like I need to suppress my excitement at this point. It's probably getting a bit annoying. It's just so incredible. Next project, a robot that places the wires. Single core are quite annoying to strip down, but works perfectly with this ancient device. By the way, was Ben also using blue wire? Yeah, that's blue, right? Okay. Then 3 is pin 11. So from here to each of these NOT gates have 6, but we only need to use 4, right? So we don't actually need to go on to the other side. We can stay up here and connect the upper ones. So we can connect, I guess we also use the left and the right one. So A is pin 13. So here and cut here. Oh, what would be cool if I add to the add wire that it makes a screenshot from the stream. Ah, no, I moved this around. I thought it would be a cool time lapse, but it probably just moving around too much, so you can't really see the wires being added. If there are some leftover gates inside the logic, you should connect the inputs to a defined level. Okay. I guess it makes sense. Does it make sense? I guess. Okay. We can do that. Oops. Pin 11. Oh, no. 11 is 3, but we want the pin 9 is the next one. So 9 goes to, in our case, 6. So 9 goes to 6, and 6 is up here. Okay. What a magical tool. Oh my gosh. I promise I stop. Add wire. How is the wire stripper doing? you don't even you cannot I cannot even express and you cannot comprehend the emotions that it's doing inside of me. Everybody should own a wire stripper. It's not a good practice if you leave them open. All right. I wonder what Ben is doing. I keep making them just like a millimeter too long always. I also have a rice cooker. I love rice cooker. Pro GJ, do you have a good like recipe? How do you eat your rice? I want to know. I want to try out some new cooking. Everybody, post your favorite recipe. What do you recommend me to make? Bonus points if it's something that boring Germans don't also know about or something. If it's like something from wherever you are from. Okay, so let's just quickly check that it's the correct order. 4 is connected to the left side here. And then 5 is connected to the right side here. And then, oh shit, we really need to remember where we connected what. I think I did this badly. Could you not just the name, but a recipe that looks fine, because otherwise you find like so many different ones. I want like one where you say, yep, that sounds like how you make it. Do I have to do one more add wire, or did I do it already? Crap, this is complicated. Okay, let's watch a bit. Oh, he's actually connecting it to the correct one. Maybe I should do that too. Just so it's consistent. So just so we can like look, for example, at the inverter chip and we know this is where the memories are connected to. 1, 2, 3, 4. Instead of like the left one, then up here, and then we go up, and then there. Maybe I undo this. Red cabbage in a cake pan and puffy pastry and pour egg white over it. That sounds amazing. What I'm building today, the RAM module. We are on the RAM module. My way is cleaner. Now I'm not sure. Chat, if I do it this way, you really need to make sure that I don't screw that up. Okay. You need to help me keep track. Okay.
So in the last video, we looked at the J chip here. So these are the inputs, input for 1, 2, 3, and then 4 up here. So that just corresponds to these inputs on these inverters for these, and then this one up here. And we're not going to use these two. So next I'll do the same thing for the second pair of chips. Yeah, I saw there were a few people that commented on the last video asking, why use the 74 LS189 when you've got to hook these inverters up to it, and it's it seems a little bit inconvenient, and yeah, it is a little inconvenient. It doesn't seem terrible, but I looked and there was a 74 LS219, but I couldn't seem to find that anywhere. But if you get your hands on one, that one doesn't require the inverters. And yeah, there's other chips too. I just didn't do a ton of research to find the absolute best chip. I'm just kind of using what I've got available. But if you've got if you want to find a different chip and use that in yours, I definitely encourage you to do that. Definitely. Hopefully these videos are kind of inspiring you to try some of your own things. Because if you if you want to build this and make some modifications to it, not only are you going to probably learn more by trying your own modifications, but you'll be even more proud of what you've built when you're done. But in any event, now we've got our all of our outputs of our 74 LS189s hooked up to our inverters. And so now we should, somewhere in here, have inverted, or actually uninverted outputs now from our memory. So of course we want to be able to see what's going on here. So
how many wires are done? Well, that's what the wires command is for. You already saw in chat 12. ProGJ, your explanation is nice, but I have something like with some sauce. What does some sauce mean? Like a sauce makes a meal. Sauces require proper, what kind of spices you put in, how much. And that makes the whole meal, Like I know that I can fry some vegetables and I know that I can do some meat and whatever, but the sauce is what gives it then later the taste and the spices, So that's kind of what I'm looking for. I've been following you on YouTube for a bit longer and just saw that you have a Twitch channel. Yeah, we just recently started streaming. We could name the wires. Yeah, maybe dedicate each wire to a subscriber. And I refuse to add the next wire until somebody is subscribing again. Maybe I should count. I think I have like just over I have like 107 subscribers, so we need to count now all wires, and if I'm down, if I don't have enough subscribers for each wire, we are waiting until we reach that point. That would have been like a good way to exploit this, attempting to exploit the system to get subs. Okay, let's connect the next one. Basically this one is connected the exact same way, so that's simple. We can just measure here the length. One sub, one wire, trying to hold chat hostage. Oh, now I need to look up a clip. Let's see if I quickly find it. I think I found the clip. Oh, I just closed my chat accidentally.
Not ugly, dude. I'm pretty. Why the fuck hasn't anybody donated yet? You guys think I stream for free? No. I'll get offline right now if I don't get a donation.
You're up. What a legend. Thanks for the Twitch Prime sub, Lone Wolf and Inferno Deity Infinity. Thanks. See, it works. It works. Europe uses now that clip as an alert for when somebody donates. It's he's cool. I like his streams. I don't have G&D wires yet. Yes, that is a that could fail. We had, I'm not sure if you were there when we had that case on stream, but I failed with that before. Like, I think it was with the clock module or the first first register or so. I forgot it and it wasn't working, and I was we tried to debug for like half an hour or so. We are 2 wires behind. Oops. Are you sure? Two wires behind? Or with that 2 wires? Crap. I don't know anymore. So from here, why do I keep making them just a bit too long? Why does this always happen? No problem though, got a wire stripper. First time stream, can you vary your wire colors more to help keep track? For the counting the wires, you mean? Well, we do vary with the color based on purpose of the wire. So I prefer to keep the colors of the wires still too long. Keep the wires to their purpose, and so all of these should be blue. Otherwise, it would look like crazy later. We are at 1.38 milliwires per second. 5 hours, 5 wires per hour, that's not too bad. Thinks it doesn't look crazy yet. So you should add a button for add wire. Yeah, I should. Wait. I actually don't know. Is the stream... Is there a stream elements integration for thing, or would I do this with just writing a chat? I guess just writing a chat message, right? That's how I would do that. Let me do that really quick. Stream Deck. why don't you have low latency enabled? That's a good question. I don't know. I haven't thought about that. Twitch chat message. Add wire. I quickly need to. No, it's fine. Okay. Now when you make a mistake, it will come to our screen almost instantly. Wait, what? What was the end result of this 8-bit computer? What do you mean? We are still working on it. For a while. Could you add the close-up camera? Yeah, you're right. Sorry. What will it do when it's finished? It does what a computer does. It will execute stuff. It can run programs like every computer. I mean, it cannot run the same programs like your real computer runs, but it can run some programs. Why do we do it then if it cannot run League of Legends or Fortnite? Why do we care? Well, we are nerds. We have fun with stuff like that. Add wire. There we go. Will it run to? I need to start making statistics. How old are you, Nerd Rage 9? Oh, you are from 92, I assume. There's either questions if it can run Doom or Crysis, and I wonder if that correlates with age or not. And then we add here to, oh wait, I made this one way too long, didn't I? Oh, 2-second pin from here to here. Just again a bit too long. Okay, now it should have the good length from here to here. There we go. It will not have megahertz. It will have hertz. Maybe kilohertz. Definitely hertz. Okay, we added the inverters. So we are approaching the 3-hour mark. I said I didn't want to stream too long today. Let's wrap it up. We hooked up these wires here. We made good progress. We had some unboxing today. Let's finish off with another test run of our computer for those people that have joined later and haven't seen it in action yet. And we can also have another look edit with the thermal camera. I think that would be fun. So let's do this really quick before we wrap up the stream, and then we can continue tomorrow. Give us another makeup tutorial. It's coming. Subscribe to Live Overflow 2 if you are interested in makeup tutorials. Okay, so this has been now off for quite a bit, right? Let me turn this here and remove that. So like that maybe. Okay, so there you can see it's pretty much everything kind of same temperature. We have a bit of fluctuation. It's a bit cooler back there, a little bit warmer closer to me. That's because right above here we have like cool air coming in from that vent here. But you can the temperature is like very minimally different. You can see the temperature scale is right now going from like 26 something to 29. So it's very minimally. It's just adjusting the colors to like max and minimum. So we can maybe put that static fixed to something that makes more sense. So here you can see it's all like 28 degrees right now. You don't see anything. Now let's turn on the CPU, and now pay attention, okay? You will we should see some stuff happening. So power's on. You can see it blinking. It's executing. And see how these chips are slowly heating up? They get like yellow. They get warmer and warmer. I don't think that we get excited easily. This is quite some crazy shit we are doing here, I think. You know, wire cutters are very rare ancient tools. It's not easy that you can find a good one. And thermal cameras are also quite a crazy thing not many people have. I think we get excited with very complex stuff. Jumbron, you can also write it to me on Twitter or per mail. I would really appreciate that. Thanks for the recipe. And if we keep that running a bit longer, it will might even get a bit hotter than that. We can maybe increase the clock speed, and then maybe it will get a bit hotter. Maybe, I don't know. But yeah, you can clearly see that when this computer is turned on and these chips are working, that they are heating up a bit. And you can also see the LEDs there on the left to heat up a little bit. What's the Bitcoin hash rate? Yeah. I mean, it's an ASIC almost, right? You know the speed of ASICs. The heat is mostly coming from driving the LEDs. Yeah, I'm sure about that too. We can also change crap. No, back. I make the same mistake all the time. We can also like change the color. We can also do like this view here. The chips are not yet hot enough. Alright, there we go. Yeah, pretty cool, right? Make a water cooler. Yeah. Okay, I think that marks a good end. You guys have a materials list? Yes, this is part on Ben Eater series. You can find the list of stuff on his website. It's there in chat. Wirecoin. Okay, yeah, so that concludes today's stream. No, I don't have Discord, or I don't have a Discord. Thanks so much for hanging out with me again. Thanks for coming back after yesterday. We have retained like 200 viewers almost consistently throughout the stream, so that's pretty amazing. Thanks for hanging out with me. Thanks for everybody who just stumbled into this Just Chatting stream, not coming from my YouTube channel or whatever, and just hung out with us nerds for a little while. I think you are awesome. And that's it. I will leave you with some outro music, and I will take on my go into the AFK screen, and then I will look up somebody to host. If you can recommend somebody that we should host, let me know in chat. If you know somebody who is like streaming, like programming or some technical stuff, and you know somebody you want to be hosted right now, let me know in chat, and I will set that up. Thanks for hanging out with me. Should be here tomorrow again. Not quite sure the time yet. Probably similar though. That's it. Yeah. Thanks. See you tomorrow. Bye bye.